Section 3.4 is solving inequalities with addition and subtraction. Learning target: I can graph inequalities and solve inequalities using addition and subtraction. An inequality is a statement formed by placing an inequality symbol, so a less than, a greater than, a less than or equal to, or a greater than or equal to, between two expressions. So for example, y plus 5 is less than or equal to -6. That's an inequality. The solution of an inequality with a variable is a set of all numbers that produce true statements when we plug them in for our variable. We can show the solution of an inequality by graphing the inequality on a number line. So here are some examples. The inequality x is less than 3. We can say all numbers less than 3 is our solution. And on a graph, we have an open circle at 3. We didn't fill it in because it's not equal to. That's just our border. It's called a boundary point, and it splits our graph from all the things that are solutions to all the things that aren't. So since we want numbers that are less than 3, we pick numbers like 2 and 1, and that's the part we shade. So everything in red there is our solution set. Y is greater than 2. We can say all numbers greater than 2. And again, open circle at 2 because 2 isn't greater than 2, it just splits the graph. Everything to the right of 2, though, is greater than 2. 2.1, 3, 5, 7 million, okay? Everything in red there, and that's what that arrow indicates, is that it goes on forever in that direction. So eventually we would get up to that 7 million. Z is less than or equal to 4. So all numbers less than or equal to -4. Remember, our variable represents all of our solutions. So here, if we look, our circle at 4 is filled in because it's equal to 4. 4 is an answer as well. So since we filled in 4, it tells us it's equal to, and we want numbers that are less than 4 as well, so we shade to the left. N is greater than or equal to 2. All numbers greater than or equal to 2, we fill in the 2 because it's equal to 2, and we want numbers greater than that, like 3, 4, and 5. So in example 1 here, it says writing and graphing an inequality. The freezing point of water is 0 degrees Celsius. At temperatures at or below the freezing point, water is a solid. Ice. Write an inequality that gives the temperatures at which water is solid. So again, we're looking for at what temperatures do we have ice, and then graph the inequality. So our temperatures is what we're looking for. Temperature at which water is a solid. So I'm going to use T for temperature. We want to know, when is water solid? So at temperatures at or below. So when it's equal to 0 and when it's below, which means less than. So temperatures less than or equal to 0 makes us have ice. Now we want to graph it as well. So on my number line, I'm going to put 0. I also want to have at least one number on each side of 0. Okay, so the next number up, the next number below. And if you don't already have 0 on your number line, throw 0 on whichever side it needs to be. It doesn't necessarily need to be to scale. Like if this was 100 and 101 and 99, you could just put 0 over here. It doesn't have to be to scale, but I do want to know which side 0 is on, because 0 is a good point to help us check. So I have all my values on my number line. Now I put a 0 at my value here. Since it's equal to, I fill that circle in. And then, since it's less than, we want numbers like -1. So we shade to the left. -1 is less than 0. So we shade on that side. So my inequality is here, and my graph is there. We can use the following properties to find the solutions of inequalities with addition and subtraction. Using these properties, we can write equivalent inequalities, and those are inequalities that have the same solution set. So the addition and subtraction properties of equality are very similar to the addition and subtraction properties of equations. By adding or subtracting the same number on each side of an inequality, we make equivalent inequalities. So, here in example 2, make sure that both sides of our inequalities are simplified. M plus 5 can't get any simpler, and neither can 10. So then, I check. My variable is being added by 5, and just like with equations, I can get rid of addition by subtracting. So as long as I subtract on both sides, it stays equivalent. 5 minus 5 gives me 0, perfect. 10 minus 5 gives me 5. Here I did not change my inequality or my variable. Keep my inequality as greater than or equal to. So that is my solution. Now we want to graph and check. So when we go to graph here, I'm going to put 5 and a circle at 5. I also want to have the next number bigger, the next number smaller, and approximately where 0 is, which side it's on. 0 is to the left of 5. We want greater than or equal to. The equal to part here means I'm going to shade in my 5, shade in that circle. The greater to part here means I want numbers that are greater than 5, like 6, for example. So I shade on the side of 6. To check our solution, we're going to check two things. We're going to check that boundary point. So I'm going to take my 5 and plug it in. 5 plus 5 should equal 10. Okay, we're going to check the boundary point. It should be equal 10 equals 10. That makes sure my point is on the right side. Now, to make sure we have the right greater or less than, okay, I'm going to take my 5 and I'm going to pick a number on each side. So here, I shaded on my right side, so I said my solutions are 6 and bigger. So I'm going to check that 6. 6 plus 5 is greater than or equal to 10. I get 11 is greater than or equal to 10. That checks as well, so we picked the right side to shade. Our solution is correct. In example 3, we're going to solve using addition. So here, my x is being subtracted by 12. I get rid of that by adding 12. And whatever I do to one side, I do to both. It gives me 12 minus 12 is 0. Negative 10 plus 12 is 2. I bring down my inequality and my x. Now we graph. Number line. I put 2 and a circle at 2. Then I pick numbers on each side. 3, 1, and I want to make sure I have 0 on there as well. We said, first of all, there's not an equal to there, so I don't fill in my circle. We want numbers greater than, we want 2 to be greater than our values. So 2 is greater than, is it greater than 1 or 3? Well, 2 is greater than 1. So since 1 is a solution, we shade the side that has 1. Now to check here, we're going to check two things again. I'm going to say negative 10 equals 2 minus 12. We're going to check that boundary point. Our boundary point should be equal. Here I get negative 10 equals negative 10. That's true, so our boundary point is right. Now I'm going to check to make sure that we have the right inequality. So again, I'm going to take the negative 10 greater than a number minus 12. We picked numbers like 1 and 0 in our shading. So those are the ones I'm going to check. I'm going to check 0 because that's an easy one to calculate. Negative 10 is greater than negative 12. That's true. So our shading is right, which means our answer's good, and so is our graph. There's our inequality, and there is our graph. Here, my variable is being added by 7, so I get rid of addition by subtracting. Anything minus itself gives me 0, and 3 minus 7 gives me negative 4. I did not change my variable, and I did not change my inequality. Now, we're going to graph it. Draw my number line. I'm going to put negative 4 and a circle at negative 4. I'm also going to put a number on each side. So the next number to the left is negative 5, to the right is negative 3, and then 0 is off over here to the right. Because we don't have an equal to, I don't fill in my circle. Then I have greater than. So I want numbers that are greater than negative 4. Numbers like negative 3 is bigger than negative 4. So I shade everything on the negative 3 side. Then I went ahead here and checked both my boundary point and my shading. I plugged in negative 4 and set it equal to 3. Negative 3 equals negative 3. My boundary point is right. It splits my graph evenly. Then I plugged in one of our solutions. I picked 0 because it's easy to add with. Got 7 is greater than 3. That's true. So we are correct here with both our solution and our graph. In 2, my variable is being added by 4. I get rid of addition by subtracting. And as long as I do it to one side of my inequality and the other equally, we get equivalent inequalities. 10 minus 4 is 6. 4 minus 4 is 0. I kept my inequality and I kept my variable. Now we're going to graph it. I put 6 on my graph, circle around it. I put the next number bigger and the next number smaller, and then I always want to have 0 on my graph as well, just as a frame of reference. Now, because I have this little equal to line, we're equal to 6 and we fill it in. Then I want 6 to be greater than my numbers. 6 is greater than 5 and 0, so I shade everything on the side of my solution. If one number is a solution, that entire side is. That 6 is my boundary point. It splits it into all of them that are versus all of them that aren't. Now to check, I set my variable in an equals equation. I got 10 equals 10. That means my 6 is the right boundary point. Then I plugged in one of my solutions. Here I picked 0. So 0 plus 4 is 4. 10 is greater than 4. We have 6 is greater than y. 10 is greater than or equal to y plus 4. So since when I plugged in one of my solutions into my original equation, I got a true statement. Our solutions are correct, both my inequality and my graph. On 3 here, my x is being subtracted by 9. I can get rid of subtraction by adding, and if I change one side, I have to change both in order to keep these as equivalent inequalities. Negative 6 plus 9, subtract, give the sign of the bigger number. Negative 9 plus 9 is 0. I didn't change my inequality, and I didn't change my variable. Now we're going to graph it. 3 is my boundary point. It's where it splits my graph into all solutions versus all not. I put a circle around it. The next number bigger is 4, the next number smaller is 2, and then I make sure I have 0 on there, on the right side of wherever it is in relationship to my value. I look at my inequality. I have an equal to line, which means I fill in my circle. And I have 3 is less than my numbers. Well, 3 is less than things like 4. So I shade the side that has 4. If one of my values is a solution, they all are. Now I did the checks here. I plugged in that boundary point 3 to see if both sides were equal. I got negative 6 equals negative 6 when I plugged that into my original equation. Since it's equal, I know that that's the right boundary point. So I know my 3 is right. Then I wanted to make sure that I shaded right and had the right solutions. So I checked. I plugged in 4 since we said 4 was part of our shading, part of our solutions. When I did that, I got negative 6 is less than negative 5, which is also true. So we know that both our inequality and our graph are correct. And I'll finish this section in another video.